Hello and welcome to the fourth in a series of 6 films about the standard level kinetics topic. Here we're going to be looking at the second theory after collision theory, which we covered in the third film. This one's called Kinetic Theory. Okay, so hopefully by the end of this film we'll be able to use kinetic theory to explain the behavior of particles in solids, liquids and gases, and that should be quite a basic thing. And hopefully we'll also be able to understand what we mean by a Maxwell-Boltzmann distribution and what it tells us about the energy of particles in a sample of gas. This can be a little bit more difficult and it's potentially confusing because these distributions can look a little bit like other graphs we've seen in other topics. Anyway, let's start off with the basics of kinetic theory, which a lot of us will probably already know even before we started the IB Diploma course. Okay, and that is that as the energy of particles increases, they will behave differently. Okay, so particles that don't have very much energy, they will come together as a solid because there are forces of attraction between them, and these forces of attraction, if the particles don't have a lot of kinetic energy, will be able to hold the particles very closely together in what we call a solid lattice. Now if you increase the kinetic energy of the particles a little bit, they'll be able to overcome some of these forces of attraction, but if they didn't overcome them completely, that is to say they were still held together by them, but they were able to move, right? So in other words, to break free from this lattice, then they'd become a liquid. And then if you increase their energy even further, then they would now have so much kinetic energy that as they moved past one another, the forces of attraction wouldn't really be able to hold them together anymore, and they would evaporate, they'd turn into a gas. Okay? And really I suppose these are the 3 states of matter that are most important to us in the IB Diploma course. But if you increase their energy even further, you could end up in another state of matter which we call a plasma. And now the particles have got so much energy that their electrons have actually started to come loose from them. And this is a bit like a gas that behaves a little bit like a metal in that it can conduct electricity. But we're not very worried about plasmas here. Okay, so really what we're trying to do here is really just to describe how the kinetic energy and the forces of attraction will cause particles to behave differently, that is to say, turn them from solids into liquids and into gases and back again. Okay, so if we move on now and we look a little bit more in depth about what kinetic theory tells us, we'll see that we actually make some assumptions about particles in the kinetic theory. And most of these assumptions can't really be true, okay, but they're close enough to being true that we can kind of get away with making these assumptions. And the nice thing about making these assumptions is that laws work. Okay, so for example, we make the assumption that particles take up absolutely no space, and this is really important in the gas laws, because this leads us to believe that it doesn't matter what gas we have, the volume that a gas will take up is purely down to the number of particles. So the actual size of the particles is insignificant. And this really works quite well until you get to very high pressures or very low temperatures, when the particles get very close together and their volume becomes significant. But it's an assumption that we make. Okay? We assume that collisions are perfectly elastic, which again can't be true, but it's close enough to being true that we can assume it. Particles move in straight lines. Particles do not attract one another at all. Okay, now that might sound a little bit odd, bearing in mind what we've been saying about solids, liquids and gases, but if the gas laws are going to work under normal conditions, then this is a perfectly reasonable assumption to make. Now, most importantly for this kinetics topic, we also assume that the kinetic energy of particles is proportional to their Kelvin temperature. And this is by far, as I say, by far the most important part of kinetic theory as far as standard level kinetics goes. So, let's look at how that relationship can be represented using something called a Maxwell-Boltzmann curve. Now, this curve, it's worth explaining how we what this curve kind of describes first of all. Now if I went around, perhaps in a very tiny little craft of some description in a sample of a gas, and I looked out of the window, and every time I saw a gas particle go by, I kind of stopped and I measured its energy. And by the time I measured the energy of all the particles in this gas, I could come back to my, I don't know, my base, and I could collect my results together. Maybe if I've had a very technologically advanced base, I could plug my results into a computer and it would come up with a curve like this for me. And what this curve would be describing would be the probability of finding a particle with a certain velocity. Okay, now bear in mind that kinetic energy, the kinetic energy of anything, is equal to a half mv squared. Okay, so the velocity of a particle has to do with its kinetic energy. Okay, so the higher its velocity, the higher its kinetic energy. Right? It is not at all likely, that is to say, there is a zero probability of finding any particles with no energy. So these curves will always start at the origin. Okay? They'll peak at something which we could describe as the most probable velocity or the most probable kinetic energy, and then they will fall away again. They'll go past this root mean squared velocity. We won't worry too much about what we mean by that. It's a bit like an average or a mean, but it kind of a statistician will tell you that it kind of deals with negative values as well as positive ones, but we won't worry about that too much. Okay, so after this most probable velocity or most probable kinetic energy, the probability of finding these higher energy or higher velocities then falls away. But what we'll notice is that at any temperature there is some probability of finding particles with very, very high energies. Okay, so this graph kind of tails off, but it takes a long time to hit the x-axis. Okay, so at any temperature there is a chance of finding particles with very, very high energies. Now, if we look at what happens when we change the temperature of a sample, we'll see how our distribution changes. So a distribution is a way of describing how the energy of particles is distributed amongst the particles in those samples. Okay, and this has got slightly different axis labels here. We've got a number of molecules with a particular energy here, but hopefully you can see the sort of parallels between this graph and the last one. Okay, and when the sample is cold, as we know, there are no particles with no energy, and then there's a most probable energy, which we could, I suppose, mark on our x-axis. Okay, and then there's particles with very, very high energies. What happens when you warm the sample up? And this is a really important thing to actually remember, because quite often you can be asked to sketch what happens to a Maxwell-Boltzmann curve if you increase or decrease the temperature. Well, as we'll see in the warmer sample, again, there are no particles with no energy. This is really important, okay, that we will never find any particles with no energy, and so these curves always start at the origin. Okay, there's now a most probable energy which is higher than it was in the colder sample. Okay, so this graph will peak at a higher energy, but at a lower number of molecules. Now, I won't go too much into any kind of calculus here, right? But what we should appreciate is the fact that the area under this curve is related to the total number of particles. Now, if all we've changed is the temperature of this sample, then the number of particles is the same, and the area under the curve must be the same. So if you pull this curve over this way, then the hump must invariably come down in height. Okay? So, in other words, as you warm the sample up, there will be fewer particles with this most probable energy, but the most probable energy has increased. And what we can also see is that this curve only crosses the other curve once. It will never cross the colder temperature curve again. Okay, and that means that there is a much greater probability of finding these higher energy particles. In fact, what we could also do, and we'll do this later on, is we could compare the area under the curves beyond a certain energy, and we can see that the area under the curve when it was cold is much smaller than the area under the curve when we've warmed it up, and that means that there are fewer particles with high energies when the sample is cold. Okay, so that's about it for kinetic theory and Maxwell-Boltzmann curves. Just make sure that in your notes, or when you're getting ready for a test or an exam, you know that kinetic energy is proportional to temperature, and that we can describe the kinetic energies of the particles in a sample of a gas using something called a Maxwell-Boltzmann curve, and you can sketch how those curves change when temperature changes. Okay, so hopefully by the time you've watched this film, which you have now, you can use kinetic theory to explain the behavior of particles in solids, liquids and gases, and you can also understand what we mean by these Maxwell-Boltzmann distributions. If you've got any questions or comments, please feel free to come and see me or to post a comment on YouTube.